Okay, it seems like we've had a campus-wide outage. We've been doing so much video streaming that we have finally taken down the internet. But luckily, we only had a little bit left for the example, which I'll continue here. We're discussing the inertial moment at D from this horizontal bar DEF. So about D, we have mass of that component, which is 1 kilogram. Okay, DF is 1 kilogram. Multiplying the length, that is 0.45 meter square, divided by 3, because we're using the mass moment inertia about the left end. This is ID, okay? Multiplying phi double dot, as we derived earlier, phi double dot is z double dot divided by 0.45. That is equal to 0.15 z double dot. Okay, so this is the inertial moment of the bar DEF. And again, there's the inertial force, but it's not going to contribute to the virtual work. We can just leave it there. The last piece we've left is the inertial force by this additional mass at E. That is looking at that is this UE that we discussed earlier. Okay, so the acceleration corresponding is going upward, and this is the amount of acceleration. So this is, I call this going downward. We call this FIE, inertial force at E. And FIE is equal to the mass of E, mass of that 0.7 kilogram at E multiplying UE double dot. Okay, so that's 0.7 multiplying UE double dot, as we worked out earlier, is 7 divided by 9 Z double dot, and this is 0.5444 Z double dot. So this should be the complete free body diagram. We have all those forces and moments. We can also give a name. This is the spring force, FSA. I can call this FS is at C, if you like. The spring forces. This is a force system that should be in equilibrium, and we're looking at all those forces and moments applied on the entire system. So the force inside the link CF is internal, and that's the beauty of this virtual work method. We don't need to be concerned with it. Now we need to go through this entire free body diagram and imagine that we have this virtual displacement delta Z happening. How much work is done by every one of those forces or moments, and their summation has to be equal to 0, because from D'Alembert's principle we have this force system that should be in equilibrium. And just to be sure, theta double dot, phi double dot, all those are coordinates Z. They change with time, but at one instant of time we have this equilibrium of this force system. This for free vibration. We have only elastic forces and inertial forces and moments. There's no external force. So going through those quantities one by one, we can maybe start from the top. Okay, there's this spring at A first, the spring force FSA. I just realized I had a little mistake here with respect to the drawing. Okay, so A should go down. Let me redo this part. I have this the initial axis, and the rotation should be about B. So my apology for the mistake. Okay, the right side goes up by delta Z. Now in this picture, when the right side goes up by delta Z, the left side goes down by this is 50 versus 300. Okay, so the left side needs to go down by delta Z divided by 6. Okay, so remember that is A, B, C. Length of AB is 50 millimeter. Length of BC is 300. So that's 1/6. And FSA, okay, I can try to use this space here, is KZ divided by 6. K is 5,600 newtons per meter, multiplying Z divided by 6. Okay, so that is 933.3 multiplying Z. So FSA is 933.3 multiplying Z, multiplying the work done by this FSA along the displacement is delta Z divided by 6. The work is negative. Okay, everything is going to be negative in this case. So it'll just be a negative sign in front of everything. This is FSA. The work done by FSA. Then we have work done by MIB. This is MIB. Again, MIB is clockwise, but the rotation is counterclockwise. So the quantity of this rotation is delta Z divided by 0.3. And the quantity of this virtual rotation is delta Z divided by 0.45. Okay, while we're at it, let's also mark this displacement at E. So that is 7 divided by 9 of delta Z. So those are all the kinematics or the geometric analysis in this under this virtual displacement delta Z. Okay, going back to MIB. MIB is 0.1031 Z double dot. The work again is negative, multiplying the corresponding angle, and the corresponding angle is delta Z divided by 0.3. So for the reactions don't do any work. Next piece is this F at C, spring force at C, which is F at C is equal to K multiplying Z. So that is simply 5600 multiplying Z. So that's the force. It does work along delta Z, or negative work for that matter. So minus 5600 Z multiplying delta Z. It's negative work done by spring force at C. The next is inertial force at E. So work is again negative 0.5444 Z double dot multiplying the distance that FIE does work along is 7 divided by 9 delta Z. Okay, the final piece is this MID, inertial moment at D. And that again is negative work. That is 0.15 Z double dot multiplying the angle delta Z divided by 0.45. The reactions and this vertical inertial force, again, none of those doesn't work because there's no displacement under this virtual displacement delta Z. And let me do a final double check, make sure that I have all the terms covered correctly. Okay, so over here, it's the same trick as we did previously. Realize that all the delta z's drop out from the equation, and our final equation of motion for equation of motion for free vibrations. So that is 1.1004 if you like, the double dot. Okay, that's function time plus 5.6 Z of t is equal to 0. So this is free vibration equation, and this is under this so-called generalized coordinate Z. Again, you have this concept of generalized mass and generalized stiffness. In the next chapter, chapter number 2, we'll be studying mu double dot plus k u dot of t. Okay, without damping first. We'll be studying this free vibration under initial displacement u of 0, or under initial velocity u dot of 0, or both. We'll study how a system like this responds, and mathematically, of course, those are the same problem. You could have a initial displacement z of naught, or initial velocity z dot of naught, and you let the system go freely and vibrates on itself. This is the equation that describes the dynamics. Right, so this should be the end of the problem. I hope that you will have a chance to finish this part of the video as well after the class today. Okay, so we'll continue next Tuesday over blue jeans.